Module 4.2, Standing waves in a tube open at both ends. We've already talked about standing waves in a string. And when we talk about the string, we've got nodes on either end. And for the fundamental frequency, we have one antinode and nodes on the ends of either side. Remember that a node means that there is no change, and an antinode is where there's maximum change. We're going to look at how air molecules work with nodes and nodes, but we have to go to a website to do that, so let's do that right now. Here we have a representation of a tube that's open at both ends. The dots moving in and out represent air molecules. If you take a look at the ends, we notice that the air molecules are moving quite a bit. There's no barrier to prevent them from moving in and out of the tube, so they move freely. If we look at the center, we notice that there is very little, in fact, there's no movement of the molecules at the center. We can see this graphically as the change in displacement. There's no change in displacement in the middle, and there's a great displacement of change at either end. This is all very nice. It visually makes us understand how things work. The only problem here is in the field of acoustics, we don't really care about the change in position. We care more about the change in pressure, because it's changes in pressure that correspond to what we hear. So the change in pressure can be represented by how far away that the molecules stay from each other or how close they get. If we look here at the outside, we notice that the molecule's spacing stays constant, which would mean that there's no change in pressure, and that's represented by a node here in the change in pressure graph. If we go look at the center, we see right now that they're spread apart a lot, and as they come in, they get really close together so that there would be a greater pressure. And so what we're seeing in the middle is a very large change in pressure. This corresponds to a node on the outside and an antinode in the middle. And so what we will come to understand is that for any open end in a tube, there is always a node. So to review the important points, at an open end, we always have a node. So this would be a node, this would be a node, and this would be an antinode. We have a node here and a node here and an antinode here. Does this look at all familiar? It looks just like the string. And so as it turns out, the standing waves in a tube open up both ends look exactly like a string, except what we're looking at here for a string is displacement. What we're looking at for a tube is pressure change. So at an antinode, we have a maximum change in pressure, and for a node, we have no change in pressure. The good news about all of this is we have a formula. Yay! The formula for standing waves in a tube open at both ends is F equals NV over 2L. No square root. Yay! All right, so this is velocity, and this is wavelength. The 1 over 2L is for the same reason that 2L is our wavelength for a string. This represents half of a waveform. This represents half of a waveform. So this is L, and this whole thing here is lambda. And this all comes from f to the n equals n times v over lambda. Lambda is 2L. V is the speed of sound in air. One more thing regarding a tube open at both ends. Just like a string has many harmonics, so does a tube open at both ends. We have here the fundamental frequency. You can look at the top diagram or the bottom curve. This would be the second harmonic, the third harmonic with 3 antinodes, fourth harmonic with 4 antinodes, the fifth harmonic with 5 antinodes, and so on. To review, open ends of a tube are always pressure nodes. The frequency of any harmonic of a tube open at both ends is NV over 2L, where N equals the harmonic number, V equals the speed of sound in air, and L equals the length of the tube. The wavelength for any harmonic equals 2L over N, and the frequency of any harmonic is N times the fundamental frequency.